students, today's topic of discussion for this class is Carnot cycle, Carnot's theorem and absolute thermodynamic temperature scale.
Next come to the point that is reversibility and irreversibility. The second law of thermodynamics enables us to divide all the process into two classes, that is reversible or ideal process or irreversible or natural process. A reversible process is one in which it is performed in such a way that at the conclusion of the process both the system and the surroundings may be restored to their initial state without producing any changes in the rest of the universe. Let the state of a system be represented in the xy coordinate here, and it is represented by A, and let the system be taken to a state B by following the path AB. If the system and also the surroundings are restored to their initial states and no change in the universe is produced, then the process AB will be a reversible process. In the reverse process, the system has to be taken from state B to A by following the same path BA. A reversible process should not leave any trace or relic behind to show that the process had ever occurred. A reversible process is carried out infinitely slowly with an infinitesimal gradient, so that every state passed through by the system is an equilibrium state. So a reversible process coincides with a quasi-static process. Any natural process carried out with a finite gradient is an irreversible process. A reversible process which consists of a succession of equilibrium state is an idealized hypothetical process approached only as a limit. It is said to be an asymptote to reality. All spontaneous processes are irreversible. Time has an important effect on reversibility. If the time allowed for a process to occur is infinitely large, even though the gradient is finite, the process becomes reversible. However, if this time is squeezed to a finite value, the finite gradient makes the process irreversible. So, what are the causes of irreversibility? The irreversibility of a process may be due to either one or both of the following, which is lack of equilibrium during any process and irreversibility due to dissipative effects. So, lack of equilibrium during any process includes heat transfer through finite temperature difference, lack of pressure equilibrium within the interior of the system or between the system and the surroundings, and free expansion of any gas. And the irreversibility due to dissipative effects includes friction, paddle wheel work transfer, and transfer of electricity through resistor.
So at first I will discuss about Carnot cycle. Basically, Carnot cycle is a reversible cycle. So what is a reversible cycle? A reversible cycle is an ideal hypothetical cycle in which all the processes constituting the cycle are reversible. Carnot cycle is a reversible cycle. For a stationary system, as in a piston and cylinder machine, the cycle consists of the following four successive processes, which can be described by the picture I have shown in the figure. So the first process is a reversible isothermal process, in which heat Q1 enters the system at T1 irreversibly from a constant temperature source, which is at T1, when the cylinder cover is in contact with the diathermic cover A. The internal energy of the system thus increases. The second process is a reversible adiabatic process, in which the diathermic cover A is replaced by the adiabatic cover B, and work WE is done by the system adiabatically, and irreversibly at the expense of its internal energy, and the temperature of the system decreases from T1 to T2. The third process is a reversible isothermal process in which B is replaced by A and heat Q2 leaves the system at temperature T2 to a constant temperature sink, which is at T2, and the internal energy of the system further decreases. And the last process is a reversible adiabatic process in which B again replaces A and work Wp is done upon the system reversibly and adiabatically, and the internal energy of the system increases and the temperature rises from T2 to T1. So by summing up all the processes, we get that the first process, which is the reversible isothermal process of heat addition. So if we plot all the processes in a PV diagram, we will get the first process in which heat Q1 is added to the cycle reversibly, and the system is changing its state from state 1 to state 2. The second process is reversible adiabatic process of expansion, in which the system is changing its state from 2 to 3 and it is doing WE amount of work done. The third process is reversible adiabatic process of heat rejection, in which the system leaves Q2 quantity of heat and it changes its state from 3 to 4. And the last process is the reversible adiabatic process of compression, in which the surroundings is doing some work which is Wp to the system, and the system is changing its state from 4 to 1, and thus 1, 2, 3, 4 constitute a Carnot cycle. So our next topic is the reversed heat engine or a reversible heat engine. So in the previous class, I have discussed with you about the basic structure of a heat engine, in which the heat engine receives some quantity of heat from a higher temperature body and delivers some quantity of work done by ejecting some quantity of heat at the lower temperature body. So in this picture, the heat engine receives Q1 quantity heat from the source, which is at T1 temperature, and delivers W quantity of work by rejecting Q2 quantity of heat to the sink, which is at T2 temperature. So a reversible heat engine means that the direction of the heat and work entities can be reversed, but that will not affect the surroundings. That means if we reverse the direction of heat and work entity for the heat engine, if the heat engine is a reversible kind of heat engine, then the heat engine will act like an heat pump or refrigerator, but the quantity of the heat Q1, Q2 and W will remain same, which will not affect the universe or the surroundings. So now come to a theorem which is termed as Carnot's theorem. According to this theorem, it has been stated that no heat engine can be more efficient than a reversible heat engine operating between the same temperature limits, which is the temperature of heat addition and the temperature of heat rejection, and all the reversible heat engines operating between the same temperature limits have the same efficiency. So from the Carnot's theorem, we can say that if there are two heat engines between a source which is at temperature T1 and a sink which is at temperature T2, if this is the reversible kind of heat engine, if it draws Q1 reversible from source and eject Q2 reversible to the sink by delivering W reversible amount of work, and if we add another heat engine which is not a reversible type, and if that heat engine extracts Q1 quantity of heat from the source and rejects Q2 quantity of heat to the sink by delivering W quantity of work done, then according to the Carnot's theorem, it can be said that the efficiency of the reversible heat engine is always greater than the efficiency of the normal or the non-reversible kind of heat engine. So let's see how this is valid. This is the source which is at temperature T1 and this is the sink which is at temperature T2, and obviously T1 is greater than T2. So we are adding a normal heat engine and we are also adding a reversible kind of heat engine within the same temperature limits, that means within the same source which is at T1 and sink which is at T2. So now for the comparison of these two heat engines, we can say that the efficiency of the reversible heat engine can be greater than the efficiency of normal heat engine, or the efficiency of reversible heat engine can be less than the efficiency of normal heat engine, or the efficiency of reversible heat engine will be same as the efficiency of normal heat engine. So these are the 3 points that can be drawn generally while comparison to heat engines. But from the structure or the constructional point of view and from the application of thermodynamics, it is clear that a normal heat engine and a reversible type of heat engine is not same. That means the efficiency of reversible heat engine cannot be same as the efficiency of normal engine. So to prove the Carnot theorem, let us assume that the efficiency of the reversible heat engine is less than the efficiency of normal heat engine. So from the expression of efficiency we can write this, and if we consider that both the heat engine are drawing same quantity of heat from the source T1, then we can say that W, that is the work done by the reversible heat engine, will be always less than the work done by the irreversible type of heat engine. So now we are assuming that we have a source which is at T1 and a sink which is at T2, and T1 is greater than T2, and we are attaching one irreversible type of heat engine and a reversible type of heat engine, as I have shown you in the previous figure. As the second heat engine was a reversible kind of heat engine, we can reverse the direction. Okay, so the direction of Q2 reverse and Q1 reverse and W reverse has been reversed. That means the reversible heat engine is now drawing Q2 reverse quantity of heat from the sink, and it is delivering Q1 reversible heat to the source which is at T1. So now, as we have mentioned that Q1 reversible equals to Q1, so it can be thought that the heat released by the reversible kind of heat engine can be given directly to the irreversible kind of heat engine, which indicates that we don't need a source and this source can be eliminated. So now the status becomes that these two heat engines altogether working and producing a net work which is W minus W reversible with a single reservoir which is sink. So this is obviously the violation of Kelvin-Planck statement, as we have learned in the previous classes. That means that what we have assumed in the previous slide, that the efficiency of reversible heat engine can be less than the efficiency of an irreversible heat engine, that is wrong. That means we have left with only one choice, which is the efficiency of the reversible heat engine is greater than the efficiency of the irreversible kind of heat engine. Thus, the Carnot's theorem, that means the statements of the Carnot's theorem, has been proved. Now, what is an absolute thermodynamic temperature scale? Basically, if we consider this as a heat engine, as I have discussed in the previous slides, we can say that the efficiency of this heat engine can be written as W by Q1, which is further can be written as 1 minus Q2 by Q1. Let this equation number as 1. And also, by the second law, it is necessary to have a temperature difference to obtain work for any cyclic heat engine. We know that the efficiency of all heat engines operating between the same temperature levels is same, and it is independent of the working substance. Therefore, for a reversible cycle, the efficiency will depend solely upon the temperature T1 and T2 at which heat is transferred, or it can be written as the efficiency of reversible heat engine is a function of T1 and T2, where F signifies some function of the temperatures. So from equation 1 and 2, we can write that 1 minus Q2 by Q1 is equals to the function of T1 and T2. So from there, we can write that Q1 by Q2 equals to 1 by 1 plus function of T1 T2, and it also can be termed as a new function, which is a capital F. Now, if we consider a source which is at T1 and a sink is at T3, and we attach two heat engine, then and let this T2 is the intermediate temperature. This heat engine 1 is absorbing Q1 quantity heat from the source T1 and delivering W1 amount of work done by rejecting Q2 quantity of heat at the reservoir T2, from where the heat engine 2 or the second heat engine is drawing Q2 quantity of heat and it is delivering W2 quantity of work done by rejecting Q3 quantity of heat to the sink. Now, both these heat engine can be replaced by a single heat engine within the same temperature source and sink, and let we consider that the W3 is equals to the W1 plus W2. That means the total work that has been produced by these two heat engines is now be produced by the single heat engine, which is heat engine 3, and this heat engine is working between the same temperature source and the sink, which is at temperature T1 and T3. So from the expression that we have learned in the last slide, we can say that Q1 by Q3 equals to function of T1 T3. Now Q1 by Q2 can be written as Q1 by Q3 by Q2 by Q3. So we can write that Q1 by Q3 is the function of T1 and T3, and Q2 by Q3 is the function of T2 and T3. The temperature T1, T2 and T3 are arbitrarily chosen. The ratio Q1 by Q2 depends only on T1 and T2, and it is independent of T3. So T3 will drop out from the ratio on the equation. After it has been cancelled, the numerator can be written as phi of T1 and the denominator can be written as phi of T2, where phi is another unknown function. Since phi is an arbitrary function, the simplest possible way to define the absolute thermodynamic temperature T is to let phi of T equals to capital T. It is proposed by the scientist Kelvin. Then by definition we can write Q1 by Q2 equals to T1 by T2. This T1, this capital T1 is the Kelvin scale temperature of the source, and this capital T2 is the Kelvin scale temperature of the sink. So the absolute thermodynamic temperature scale is also known as the Kelvin scale.